So today, last thing, we're wrapping up Unit 3. So I'll finish this today, give you a work day tomorrow, and we're gonna start testing on Wednesday. I'm gonna break the test into. You'll have a little time still probably to finish up with some of this later stuff because I'm gonna give you a 2-day window, and then you can do like a makeup test next week, obviously, and you can retake these. But I want to break it up into 3 parts, and I've got 1 practice test already up. I'll put the other ones up today. The first one essentially is, and 2 of these will be really pretty straightforward and simple. The hardest one probably be the factoring one, just because factoring is kind of hard. But, first one will just be properties of exponents and graphs of polynomials. Okay, and that's it. So that's stuff that I doubt you probably even have to really spend a lot of time prepping for that one. One of them will be on arithmetic with polynomials, so the adding, subtracting, multiplying, and dividing polynomials. And then the last one will be on factoring polynomials, finding zeros of polynomials, stuff like that. Okay, which would be section 6.4, and then some of this stuff in 6.5 too that we're going to talk about today. Okay, and I'll make all of them pretty short. And here's kind of like you're used to this. Rather than giving you one great big test, so if you had to retake it, you got to retake everything. This way, it's a little more targeted. So if there's one thing, you might do great on most of it, but then maybe there's one test you got to redo, then you can just redo that one. Okay.
Can you give us like 15 tests that are just like one problem?
No, sorry, I won't do that. But I'll give you 3. I'll give you 3 that are pretty short. Okay, so for today, what we're really gonna do here is we're gonna use synthetic division to our advantage as a way to help us factor polynomials or find the roots of polynomials. So 2 theorems that come up, and these are really not a big deal. Let's just put these in context. This looks pretty mathematical, but I want you guys to be spending a little time. It's about time that you really need to be like reading the textbook a little bit. I don't think you need to read it cover to cover, but I know with all the stuff that's available with the videos and everything in here, it makes it pretty easy to not ever even look at the textbook. But we're getting into some stuff now where I really feel like you should. And here's the other thing too. I might even have to make some assignments that you just read the textbook, because there is a component of this that's also important. The ability, I know you're still a little ways away from this, but the ability to read a textbook is critical in college. That's one of the predictors of success in college, is that can you read a mathematical textbook? And it's a little different. It's not like you're reading a novel. It's the wording is different. It's very precise. There's certain terminology you got to get used to. And so, I'm putting all of the PDFs of the sections in the textbook right underneath the assignments for that section. At least open that up and skim through it. You don't have to read the whole thing, but skim through it, look at the definitions, maybe look at some examples. Just kind of get used to what it's like to read a textbook. All right, so what's this saying here? When some polynomial, which we're going to call p of x, is divided by x minus a, then the result can be written in this form is how they choose to do it. And this is how we've typically talked about it, right? The polynomial divided by x minus a is going to equal some other polynomial, some smaller polynomial called q of x, we might call it. It just stands for the answer, right? Plus, potentially, we're going to have some remainder, right? Some part that remains over the denominator, right? Does that make sense? So r stands for the remainder. The other way to write this would be, if we multiplied each side through by x minus a, we would get the original polynomial equals x minus a times q of x, which is the smaller polynomial, right? Plus, potentially, there's going to be some leftover remainder, right? They mean the same thing, but sometimes in math, it's advantageous to look at it one way as opposed to the other way. That comes up a lot, where 2 equivalent statements, sometimes the math is easier to look at and manipulate in one form than another. So let's look at this for a second, this remainder theorem. If when we divide the polynomial by x minus a, if there's something left over, then that's what we call the remainder. Now, what if that remainder is equal to 0? What does that imply? Okay, if there's no remainder, let's look at the blue form for a second. If there's no remainder, if the remainder goes away, then this is all we're left with. The original polynomial equals x minus a times some other factor. So what's that tell you now that how is x minus a related to the original polynomial? What could you say about it that's special? Say it again? No, not exactly. It's kind of an ambiguous question. Let me give you an example without algebra for a second. Let's say, we'll take two examples here. Let's say that we divide 12 by 3. What do we get? 4. So another way of saying that is 12 equals 3 times 4, right? Okay, let's compare that to what happens if I divide 12 by 5. What do I get?
12 times.
I get 2 and how much? 2/5 left over. So another way of saying that is 12 equals 5 times 2 plus 2. What's the difference between 5 and 3 in these two examples? 3 is a little more special maybe than 5 is in the way here. How would we describe 3?
3 is a factor.
It's a factor. It's a factor of 12, isn't it? Because it divides evenly into 12. How do we know it divides evenly? Because the remainder is equal to 0. Okay. So 5 is a non-factor because it did have a remainder, right? So sometimes when we talk about this factor theorem, all the factor theorem is saying is that if r is 0, then we know that x minus a is a factor of the original polynomial, right? Okay, that can be useful, can't it? Because if we know that that's one way to prove that an expression is a factor, we could use that to our advantage in actually factoring a big polynomial, right? Let's look at an example. What if we have something like this, let's say. We've got this big polynomial, it's cubic in this case, and you're going to do some problems like this. So let's read through these directions here. Determine whether the given binomial, so x plus 4, is a factor of the polynomial f of x. If the given binomial is a factor, then factor the polynomial completely. So we're going to write the polynomial in its completely factored form. If it's not, then just enter in. Okay, so how would we check? We could just divide, couldn't we? Right? We could just divide, we could see if this divides evenly into f of x. Right? So that just means we would try, we would just try x cubed plus 15x squared plus 74x plus 120, all divided by x plus 4. But we don't need to do that using long division, right? We could use synthetic here. Why can we use synthetic here? I heard a couple answers. Go ahead. One was over here. Go ahead. Okay, and I heard one over here. What was? It's linear. Okay, same thing, right? Because the factor is a linear factor, right? And we can always, if the factor is linear, we can always try synthetic division, and it's quick and easy. So we could write this instead. Now, as in that form, where my coefficients are what?
1.
15, 74.
And if it's a factor, what's going to go there? Be 0, right? In the remainder box, we get 0, okay? So what goes out front here? Negative 4, not 4, right? Because we're finding the 0 of the denominator, right? So x plus 4 equals 0 when x equals negative 4, okay? You're always putting the 0 of the factor in the little bracket, okay? So now let's do our work here. What do we do? Drop down. Whenever a number appears below the line, we multiply, right? So negative 4,
11.
add, we get 11. 11 times negative 4, negative 44, what's that, 30? So we did get 0, right? So that's helpful. Okay, so then how do we interpret this? What's that mean?
X plus 4 times x cubed plus 11x squared plus 30x equals.
close. But what are these columns stand for now? This is the remainder, so what's this column gonna be? Constant. That column is the x coefficient, x squared, etc. So remember, it's kind of, it's easier to kind of start from the right and work your way left, especially if you have lots of columns. Right, so then we could say, what this tells us so far is that this big polynomial up here, x cubed plus 15 x squared plus 74x plus 120 equals x plus 4 is a factor, right? Times that factor, right? X squared plus 11x plus 30, right? Everybody good with that? Okay. And then now we would just continue on, but now it's pretty easy. Now this is quadratic. Quadratics are easy, right? So what are our options to factor a quadratic? We could use the quadratic formula to get the zeros and then just subtract those from x, right? That's kind of our last ditch. That's a lot of work. This might be an easier one. What are we going to try to do here? Just say it again. Magic numbers. Numbers that multiply to positive 30 and add to 11 are 5 and 6, right? So then we could break this thing apart into x plus 4 times x plus 5 times x plus 6. Okay, we're done. See? Okay. So synthetic division can be really useful to you that way. Next chapter, we're going to learn a way to, without being given the zeros, we're going to learn a technique for being able to guess from a group of possible candidates. We're going to be able to guess what the zeros are, and then we can easily check them very quickly using synthetic division. That's next chapter. Okay, so something like this, then, this is essentially the same problem, isn't it? I mean, it's really identical. I mean, it's different functions. But when they say completely factor the polynomial, in the previous problem, they gave us a potential factor that we had to check. In this one, they're just giving us, this is actually easier because they're actually telling us that this does correspond to a factor. But the -9 is saying f of -9 is equal to 0. So there's really just one thing we got to do to tweak this to make it look exactly like the other problem. How could we turn this expression, or this equation right here, f of -9 equals 0, how could we turn that into a factor? X plus 9, right? So this is saying that -9 is a 0, therefore x minus -9 is a factor, right? So we get x plus 9 is one factor, and then we would just divide that through synthetically. What's going to be the degree of the polynomial we get if we divide this big f of x by x plus 9? It's going to be quadratic, isn't it? Yeah, so it's going to be the same situation as before. Either it's going to factor easily or it's not. Okay. All right, so we're not going to do that one. Okay, what about one like this? This is even slightly different. And you got to read these carefully. I'm purposely giving you a mix of different kinds of problems here that are asking for the same process, but in slightly different contexts. So you got to really be aware of what the context is. This time it's saying use the given 0 to find all of the real zeros of the polynomial. So we don't have to write it in factored form. We're just trying to find the zeros, right? Okay, so what should we do here? So, okay, so we've got this big function, right? We know that if this is a 0, we could factor out an x minus 6, right? By dividing this function synthetically and inputting 6, right? So that means then we know if I put this 6, and I don't put a -6, do I? Because 6 is the 0, right? The factor would be x minus 6. So our 6 goes out there, our coefficients are 45, -234. What happens if I'm missing a power of x? Got to put a 0 coefficient. What do I know already goes there? 0, right? Right? Okay. So I just need to know what's left over. Okay, so I bring down the 45. 6 times 45 is going to be, what, 270? Adding, right, with synthetic division. It's the opposite of long division where I subtract. So 36, 216, what's that, 80? 480, 64, 384. Okay, so they do cancel. And what does this tell me I'm left with? Okay, so there's my constant, coefficient of x, x squared, x cubed, right? So then we could just, we're left with this. We're left with that, right? So that's a cubic that now we've got to factor. We already know one of the zeros is 6. We got to find the zeros of this one. Okay? So we're really just setting this whole thing equal to 0 and solving, right? How can I do that one? Unfortunately, it looks like I can't take anything out, huh?
You could graph it.
No? No, I have an approach to this. Now, it's not guaranteed to work.
You could do the thing where you separate the first two factor by grouping.
Okay, yeah, we're gonna factor by grouping. We're gonna try to factor by grouping. And do you think, is it gonna work or not? Can you tell? You kind of start to get a feel for it. You can kind of tell a little bit. It's gonna work. And the way, in hindsight, when you look back on this, here's how you know it's gonna work. The ratio of 45 to 36 is the ratio of 80 to 64. Okay? And that's kind of how you can tell in advance that it's gonna work. So when we're all done, just go back and look at that. So we split this thing up. From the first group, what's the greatest common factor? 9x squared, good. Which leaves behind what? Plus 4, okay. So if this is gonna work, what do we need to get over here? 5x plus 4, right? Okay, what coefficient would make that happen? And let's just check to make sure. 16 times 5x is 80x, 16 times 4 is 64, right? So it works. Okay, now what? Now I just have to regroup. So I've got term 1, term 2, what's the common factor? 5x plus 4, good. So we'll pull out a 5x plus 4, leaving behind what? Okay, so then there's the other two factors. If I want to include the first factor in there, I can. The first factor is just x minus 6, right? And I'm setting this whole thing equal to 0. Okay, so what are my zeros going to be? Well, we already have this one, 6. How about this guy? Yeah, if I subtract the 4 to the other side and divide by 5, negative 4/5. What about that one?
Not real.
It's not going to be real, is it? What are some ways you know it's not going to be real? Okay, because it's the pattern it fits is a sum of squares, which is never going to give us a real solution, right? And then the other way is if you just look a couple steps in advance, if I subtract 16, divide by 9, and square root, obviously I'm getting a negative number under the radical, right? Does that make sense? One other way, which in this case is probably the worst way, would be to look at the discriminant, b squared minus 4ac. What's b? 0. There is no x term, right? Minus 4 times 9 times 16, obviously that's negative, isn't it? Okay? So those are our answers. That's it. Okay, negative 4/5 and 6. Only got 2. What about this? I just want to show you one little trick with this. Kind of cool. It's called, I call it nested synthetic division. I mean, I don't know if it really has a name. It's just something I do, and I think it's not like it's unique. I'm sure tons of people do this, but it's a good way to do it. if I'm trying to find the missing dimension, and I know that these are dimensions and that's the overall volume, what could I do really quickly to find that? I could just divide synthetically, couldn't I, right? I know that these have to be factors, right? Because that's what the volume is the product of the dimensions. So we'd end up then with, we start off with a 1, coefficients of 1, 19, 64, and negative 84. And out front we'll put, what's this going to be? Negative 6, okay, good. So bring down the 1, negative 6, 13, what's that going to give us? Negative 78, negative 14, positive 84, 0. Okay, what's that?
64 times 13.
Did I do something wrong?
You do.
Did I do something wrong? Okay. Looks right, doesn't it? Okay, now what? So here, this is how you can nest these things. So this is what we're left with. Well, just do this. And then what's the next? 0. Negative 14. Right, so I bring down the 1, negative 14, negative 1, 14, and 0. And so what does this tell us right here? X minus 1 is the other factor. So what's the other 0 going to be? Well, actually, that's all we wanted, isn't it? Never mind. Right? We just wanted to know what the other dimension is. And the other dimension is X minus 1. Okay, so the other thing I want you guys to start doing, I'm going to limit the number of takes you can do on tests in order to kind of get you thinking about being smarter on tests. So these aren't such disposable tests. Now, how could I know if I get this right? Expand it out, right? Expand it out, and if I get this answer, I know I got it right. Okay. What's that? Well, it's unlikely you're going to make the same mistake in both directions. You know, it's multiplying these together is pretty simple, right? Okay. And then last one, I won't even do this one, but how could I do this? Let's just talk about this for a second. I want to find all the points of intersection of these two curves, f of x and g of x, right? How do I find points of intersection of curves in the first place? Okay, graphing it is an imperfect way to do it, unless I have graphing technology. But even then, it's going to give me probably decimal approximations. It's probably not going to give me exact answers, right? So what if I wanted exact answers? How could I find where functions intersect? Like if I want to know, for example, let's take something easier. What if I want to know where the curve, f of x equals x squared, and the curve g of x equals 4 minus x intersect, how could I do that? Where they intersect, those are going to have to be ordered pairs that are solutions, right, of the system. What's that mean? Yeah. They have to be places where the y value, which is given by f of x here and g of x, is the same, and so is the x value, right? So really, when I ask the math gods where these intersect, I'm really just asking for all of the places where f of x and g of x equal the same thing, right? The x values where that happens. So I could just set, when I solve this, I could just set x squared equal to 4 minus x, and now the math gods are going to answer me with all the values of x that make that true, right? Those will be all the x coordinates of the places where the functions intersect. We could solve that. It's not a big deal. Let's say we did solve that and we got our x values. How would I find the y values? Plug them into either one, right? Because by definition, these are the places where the y values were equal, right? So pick whichever one looks easier, probably that one, and plug them in, okay? So what about a problem like this then? It's a little harder. I've got a cubic, polynomial, and a quadratic. And so setting those equal to each other and solving would be, you know, a little bit harder this time, wouldn't it? If I set these equal to each other, so x cubed minus x squared minus 16x minus 20 equals negative 2x squared minus 2x plus 4. right? I could make one equation out of that in standard form. How? Yeah, just push everything to the left maybe where the x cubed is, right? And then I'd end up with a polynomial equation, just like all these other polynomial equations up here, right? If I'm finding zeros, and we're just finding out where that equals 0, right? If I'm given one location of an intersection at -3, what's the significance of that x value? Yeah, what's the significance of that one, though? If I make a new equation out of that polynomial minus that polynomial equals 0, right? What's the significance of x equals -3? Okay, but what's the significance? I've got this new equation, right, where I set these equal to each other, and then I put it in standard form. What happens if I evaluate that function at -3? What am I going to get? True. Let me write this down. I just want to make sure this is kind of important. Oops, what did I just do? Thanks. So we've got this function equals this function, right? That's how we're trying to solve that equation. We want to know where the f of x equals g of x, right? So I could put this into standard form, and I'd end up with what? If I add x squared to both sides, I get x cubed plus x squared, add 2x, subtract 4. Something like that, right? So I get this cubic polynomial. The solutions of that equation are going to be the solutions of the blue equals red equation, right? Those are going to be the places where f of x equals g of x. Okay, they're telling us that one intersection occurs at -3. I could plug it in there, but I can already tell you what I'm going to get for an answer if I plug -3 in for this purple polynomial. What am I going to get? What do you think? Kirk, what am I going to get? I'm trying to find all of the places. Now let's back this up just a little bit. We're asking the math gods where these functions intersect by setting f of x equal to g of x, right? That gives us this equation. Okay. Now, once we have an equation, we can roll up our sleeves and do some algebra on it, right? Because as long as I do algebraic steps to this thing, I'm not going to change the solutions, right? So if I push all of the terms over to this side and put it in standard form, all I've done is just change the form of the equation, but I haven't changed its solutions, right? Everybody agree? So then the solutions of this equation are going to be the values of x that make this expression equal to 0, right? So what's going to happen for this one then? It's going to equal 0, isn't it? Right? Because this is x equals -3 is going to be a value where blue equals red, guaranteed, right? Because they tell us that. They tell us that that's an intersection, right? So then that's going to be 1, 0 of this. So how could I easily attack this problem and find the others? Okay, I know that x minus -3, x plus 3 must be a factor of this, right? So I can divide that synthetically then and figure out what the other bigger factor is. But what's its degree going to be? If I divide this whole thing by x plus 3, I'm going to get quadratic, right? And then finding the other zeros, it's not asking me for factors, it wants zeros. So I could just use the quadratic formula, right? I just want to know the solutions. I'm going to end up with a quadratic, call it q of x, some quadratic equation in standard form. I can find the real zeros of that every time by just doing this, right? So that makes life a lot easier knowing where one intersection is, right? Does that make sense? It's a lot. It's a lot to, I mean, it's actually not that much math, but different contexts of the same thing. Okay, so you got your assignment. I'll put up the practice tests. We'll start chugging away on those on Wednesday. I'll give you a full work day tomorrow.